it's a topic related to circular motion. Okay, so when we talk about circular motion, let's first talk about some key differences that we see between circular motion and we see between linear motion. Now, other than the obvious difference, which is that circular motion is in a circle and linear motion is in a straight path, one major difference that you will see between both circular motion and linear motion is that in circular motion, uh, in linear motion, velocity is constant, right? Assuming that the person is traveling at constant speed, we can clearly and easily say that velocity is constant. Velocity can be constant or velocity may not be constant. But in circular motion, velocity is always changing, always. Velocity is never constant when we talk about a circular motion. Question becomes why? What makes it so that the velocity cannot at all be constant in a circular motion? The reason for that is because of change in direction, right? If you talk about a linear velocity, on a linear velocity, you're driving on the road, whether you accelerate or not depends upon you, right? Whether you increase the speed, whether you decrease the speed, whether you change the directions, it depends upon you. So velocity can either be constant or it might be changing. In a circular motion, velocity cannot be constant, regardless of whether you are moving at constant speed. Even if you are moving at a constant speed of 2 meters per second, even if you are moving at a constant speed of 2 meters per second, since the direction of your movement is going to be constantly changing, and we all know velocity is a vector quantity, so velocity is always going to be changing. That's the first difference that exists between circular motion and linear motion. In a linear motion, velocity may or may not increase. In a circular motion, velocity is always changing because of the fact that despite traveling at what we can say a constant speed of 2 meters per second, 2 meters per second, 2 meters per second, despite traveling at a constant speed, the object is going to be continuously undergoing change in direction. As a result, the velocity is always going to be changing. If we can say velocity is always changing, we can then confidently say that circular motion always has acceleration. Regardless of whether there is an increase in the numerical value in the magnitude of it, because the direction is always changing, we can say that circular motion is always accelerating. In a linear motion, you may have acceleration or you may not have acceleration. A circular motion is always considered to be a circular movement. Third difference, assuming that in a linear motion, if the object is traveling in one direction only, displacement cannot be zero, right? If an object is traveling in one straight line, displacement cannot be zero. But in a circular motion, displacement can be zero when the object completes one cycle. When the object completes one 360-degree movements, displacement can be zero. But if an object is traveling in a linear motion in one straight line in one direction, displacement cannot be zero, right? But in circular motion, displacement can easily be zero. Three key differences that we see between circular motion and linear motion. Now, in circular motion, what are some of the concepts that we have to talk about? First thing that we're going to have to talk about is, I find it's easier to understand the topic if we link it to linear velocity or linear motion. Now, in linear motion, we always have displacement. So, in circular motion, we have angular displacement. It's the same thing, it's displacement, but it's angular displacement. I'll explain what this is in just a second. Secondly, in a linear motion, we have velocity. Just like that, in circular motion, we have a velocity. But in circular motion, we are going to study two types of velocity. We have what we call angular velocity, and we are going to study about linear velocity. I will go over details in a bit, but just to give you a concept, what is the difference between angular velocity and linear velocity? Angular velocity, quite simply put, is the displacement per unit time, right? Think of it in terms of average velocity. As it goes, as the object travels in the circle. So what is the displacement per unit time? The displacement per unit time that we are seeing is angular velocity. Angular, like if you, I don't know if I mentioned this to you or if I mentioned this to another student, but angular is a term that is specific to circular motion. Then linear velocity. What is linear velocity? Linear velocity is instantaneous velocity. An easy way to understand this is think of the diagram that I've drawn. Think of it this way, that you have a rock which you have attached at the end of the string and you are moving it in a circle. At one point, the string will break. When the string is going to break, the object is not going to continue to travel in a circle, right? The object is going to shoot in a straight line. It's going to shoot it's going to shoot in a straight line direction. Why? Because at every single point, the object also has a linear velocity. It has an angular velocity, which is allowing it to travel in circle, but it also possesses a linear velocity. That linear velocity, what does that mean? That means that whatever force is making it travel in a circle, whatever force is making the rock travel in a circle, if that force suddenly disappears, the object will travel linearly because the force making it travel in a circular manner is now gone. So at that point, the object is going to travel in a linear direction. That instantaneous force, angular force is like the overall velocity, right? Linear velocity is the instantaneous velocity. What is the velocity at this specific point? What is the velocity at this specific point? That is linear velocity. And the overall velocity is the angular velocity. Then, obviously, since in linear motion we have acceleration, so we also, just like that, we have angular acceleration. We call it angular, or the more commonly we call it centripetal acceleration. And finally, we obviously, whenever there is acceleration, there is resultant force. That resultant force is centripetal force. So these are some of the things that you are going to study under this topic. So let's start with angular displacement. What actually is angular displacement? So angular displacement, you already know what displacement is in terms of physics. Specifically, when we talk about angular displacement, so angular displacement is the angle traveled by the object, right? Because in a circular motion, displacement is not just in terms of 10 meters, 20 meters, 30 meters, no. In circle, when we measure displacement, we measure it in terms of angles, right? So that's what angular displacement is. Angular displacement is, I am measuring the angle traveled by an object, okay? The angular displacement is the measure of the angle through which an object moves in a circle. So angular displacement, simply put, is the angle. How much angle has the object traveled in the circular movement? That is angular displacement. Now, there are two units to measure angles. If you're doing mathematics, you probably already have studied this before. There are two ways of measuring angles. I'm saying ways, I should say units. There are two units that I can use when measuring angles. One is the traditional degrees. So we can have our 360 degrees, 90 degrees, so on and so on. The other unit for measuring angles is radians. So there are two units that we can use for measuring angle. We can either measure them in degrees. So I can either measure, for example, if an object travels from here to here. So that means that my approximately the object has traveled 90 degrees. So the angular displacement is 90 degrees. Now, the other unit that I can use is radians. What actually is radians? Radians is basically if I take my arc length and divide it by the radius. If I take my arc length and I divide it by the radius, I can find out what the angle is, but the unit is radians. I can find out the angle in terms of the unit radians. So that's what radians is. Length of arc divided by the radius of the circle. That is going to give me the angle in radians. And this is the formula for it. The theta, this theta is a symbol of angular displacement. Okay. And S stands for arc length, R stands for radius. Now, in your syllabus, you can measure angular displacement either in degrees or in radians. But you're going to find in your past paper questions, radians is the preferred unit. Most of the time, the questions are going to be asking you to answer either answer in radians, or they are going to ask you to or they're going to provide you value in radians, right? So radians is the preferred unit that we use when we talk about angular displacement. But if your answer is given in degrees, that's also technically fine. Unless, of course, the question specifies give the answer in radians. Radians is what you should choose. So there are two units that we can have for measuring angles or angular displacement. So angular displacement can either be degrees or radians. Now, you should know how to convert degrees into radians. I think Ashmesh, you're also doing mathematics, right?
Yeah, I already know how to do it.
Yeah, all right, perfect. So you should know 360 degrees is equals to 2 pi radians. Right, so I'm not going to spend time going over conversions with you. So that's your angular displacement, right? So angular displacement is simply the angle that an object is going to travel in circular motion. Now, when we talk about angular velocity, what is angular velocity? Angular velocity is the angular displacement per unit time. So if I take the angle traveled by the object in per unit time, that will give me the angular velocity. The symbol for angular velocity is, just give me 1 second, hold on. All right, so the formula for this is basically angular displacement per unit time. Now, for one complete cycle, the angular displacement is going to be obviously 2 pi. So we are going to write down 2 pi. Then our time, the time taken for one complete circle, is obviously the time period, right? The time taken for one complete oscillation, the time taken for one complete cycle is known as the time period. So one complete cycle has the angular displacement of 2 pi. The time taken for one complete cycle is the time period. As you know, frequency is equals to 1 divided by time period. So our formula becomes 2 pi f. So our angular velocity is equals to 2 pi f. Omega is equal to 2 pi f. So far, the formulas in this topic are a few, and you need to make sure you remember them because there are quite a few formulas in this topic, not just one or two, there are a few formulas. You have to remember them because for multiple formulas, we can have multiple quantities, we can have multiple formulas. So you need to remember all of them so it allows you to easily
In this
decide which
example,
formula.
did you use 2 pi as just an example angle?
No. This is the formula. This is the formula. It's not an example. This is an actual formula. Let me, one second. Let me do it again. The thing is that we have the formula is delta theta over t. I am not telling you an example. This is the formula 2 pi f. I'm showing you how the scientist or the physicist derived it. I'm telling you the derivation of it. Okay. Now, they said, let's assume that we are talking about one complete circle. Okay, this is how they got the formula. We are talking about one complete circle. One complete circle means that my delta theta is going to be 2 pi radians. Angular displacement is going to be 2 pi radians or 360 degrees. Now, the time taken for one complete cycle is the time period, right? That's the definition of time period. Time taken for one wave, time taken for one oscillation, time taken for one complete cycle. So they said, let's say that the let's say that the we are talking about one complete cycle. So the delta theta is going to be 2 pi. Then they said, let's say, obviously, if we're talking about one complete oscillation, then the time taken is going to be time period. So they said we know frequency is equals to 1 upon time period. So we can easily substitute frequency over here. So this is the formula. This is actually a formula for angular velocity. 2 pi f, and this was the logic or the derivation behind deriving it, right? They know that for one complete cycle the angle is going to be 2 pi, fixed. It's an understood fact. Then time taken for one complete oscillation is also going to be known as the time period. Another fact, frequency is equals to 1 upon time period. You substitute in the formula, so you get the formula angular velocity is equal to 2 pi f. So this is also a formula for angular velocity. This is also a formula for the angular velocity. This is the formula that you're going to be using quite commonly. Omega is equals to 2 pi f. This is the one you're going to use quite commonly. This is not used, I have not used it as such in your past paper questions. This is the major formula. And this was, I'm not taking an example, this is the actual derivation behind it, how they took delta theta upon t and got the formula 2 pi. All right, does that answer your question?
Yeah, thank
Okay. Now, when we talk about our, like I told you, we can have angular velocity or we can have linear velocities, right? Linear velocity is the instantaneous velocity or the velocity that is possessed by the object at that particular time in the circular movement, right? Now, that is what linear velocity is. Basically, an easy way of understanding it is this, that if you, I give you the example that we have tied a rock with a piece of string and we are rotating it in a circle. The moment the string is going to snap, the rock is going to fly off. So the velocity with which it is going to fly off, that instantaneous velocity, the velocity at that particular point in movement is the linear velocity. You know that velocity, constant velocity is equal to distance over time, right? And if you remember, I had told you that the formula for radians is equal to S over R, right? S was the arc length. Arc length is basically the distance, right? In this case, if we talk about the arc length, so arc length is the distance, not the displacement. It's the distance, right? So my object, if I look at the distance traveled by the object, the distance traveled by the object is this. This is the distance traveled by the object, S, the arc length. So distance traveled by the object is my arc length, S, and the formula for radians is arc length divided by the radius. If we rearrange the formula becomes distance is equals to r theta. Substitute this in the formula over here. Velocity, instead of s, instead of distance, I can write down r theta upon time. Theta upon time is equals to omega, right? Omega is equals to delta theta upon t. So V is equals to R omega. This is the next formula that you have to remember. This is the formula of linear velocity. Linear velocity is radius multiplied by angular velocity, and this is the derivation behind it. Velocity is equals to distance over time. Angle in radians is equal to distance. Distance is the arc length. Arc length divided by radius. So we get distance is equals to r theta. Substitute in the formula. Theta upon t is equal to omega. So v is equals to r omega. This is the formula for linear velocity. So far, the formulas that you should know is that angle in radians is equal to s divided by r, where s is the arc length or the distance. Then, secondly, you should know that w is equals to delta theta upon t. I'm saying w, sorry, this is a Greek alphabet, it's omega. Omega is equals to 2 pi f. Both of these are formulas for angular velocity. Then we have velocity is equals to r omega. So these are the four formulas that we have covered so far. I hope there's no confusion, right? So far, it's all clear.
Yeah, I think so, yeah.
All right. Now we come on to slightly confusing thing. Okay. The slightly confusing thing is the derivation of the equation for centripetal acceleration. This derivation can be confusing because it involves some assumptions. When the scientists were deriving the equation, they made some assumptions. They used vectors to solve it, and it's not physics, it's just maths. So let's go over the derivation of how we can derive centripetal acceleration. Now, derivation of centripetal acceleration is you need to know the derivation well, right? The reason for that is because the derivation is often asked in the exam questions, and it carries a good amount of marks, usually 5 to 6 marks. In this topic, I feel like this might be the only part that you find a bit tricky to understand because it's a lot of assumptions and it's a lot of just pure mathematics, not that much physics. Just give me 1 second. All right. So talking about how we get to the derivation of centripetal acceleration. To understand this, first of all, let's go ahead and consider a circular motion. That's not this is circular. Now, let's say that we have an object that is moving from what we call as point A to point B. Okay. Now, as the object is moving from point A to point B, we have to understand that we are talking about a topic related to vectors. Since we are talking about a topic related to vectors, so we have to take our vector components, right? Just like we have discussed before, we can divide this into horizontal component and we're going to divide it into vertical component. What are we going to divide? The velocity, right? So let's say we have 3 points, point A, point B, and then in the middle, we have point C, okay? Now, if let's say at point A, the object has a linear velocity that is going to be v. If I label this for you, this is the object's linear velocity v. Okay. Now, this linear velocity can be divided into what can be considered as the horizontal component and the vertical component, right? So this velocity, linear velocity v, can have a horizontal component and it can have what we call as our vertical component, right? Now, and of course, then we have our angle theta. This is the angle theta, let's say. Okay, the angle with the this is the angle theta, and obviously this will be our angle theta. Let's say this is the angle of linear velocity with our vertical. Then if we take a look at point B again, at point B this object is going to have a certain linear velocity, and again that linear velocity can be divided into what we consider as our horizontal component and our vertical component. This is my vertical component and this is my horizontal component. The horizontal components, if we go ahead and I write down the formulas for you, the horizontal component is going to be v cos theta, while the horizontal component is going to be v sin theta. I'm so sorry. Vertical component is going to be v cos theta, and the horizontal component is going to be v sin theta. Okay. So now, when we go ahead and we talk about it, let's write all of this down as I'm saying it because it makes calculations easy to understand. The vertical component is going to be v cos theta. The y is by y, I mean the y-axis, okay, vertical component. And on the x-axis, we will have v sin theta. Now, you can, if we talk about our the vertical component, okay? Now, vertical component, this is point C. Point, the object is moving from A to B, okay? Point C is the middle point. Now, you can see that the object is at point A and point B. The V cos theta is basically going to be equal to each other, right? Because uh, the um, the angle theta is the same, right? Above C, for example, the angle is 30 degrees. So A has also traveled 30 degrees and B has also traveled 30 degrees, right? Then, on the other hand, if we talk about V is also going to be the same because even though the direction of velocity is changing, the magnitude remains the same, right? So the value of V is the same at point A and point B. The angle is also the same at point A and at point B. The difference is that A is above C and B is below C. So since A and C is my reference point, C is the comparison point. Okay, that's where C is. the object is moving from A to B, but I'm using C as my reference point. Okay, it's the midpoint. So what has basically happened is this, that A and B are equal distances above and below C, right? Above C and below C, A and B are equally placed. The angle is equal, the arc length is equal, the magnitude is equal. So vertically, we can say that acceleration is 0 because the vertical acceleration of at A and the vertical velocity at B are equal to each other due to the fact that because I'm comparing it to my reference point, right? In perspective of my reference point, in comparison to my reference point, A and B are equally placed. So if I take a look at the velocity at A and velocity at B, I can say that they're equal to each other, the vertical component. Hence, the vertical component of velocity is 0. Vertically, there is no acceleration, right? Where is the acceleration? Acceleration is horizontally. And later on, when I explain to you centripetal force, it will make more sense to you why there is horizontal acceleration. Acceleration is horizontal. So when we talk about horizontal acceleration, so at point A, let's say that the acceleration, that the velocity is v sine theta. Point B, the acceleration is now in opposite directions. Sorry, the velocity is in opposite direction. So it's going to be minus v sine theta, right? So now, if I want to find the acceleration is change in velocity divided by time, right? It's going to be basically be A minus B divided by time taken. This is why vertically there is no acceleration because v cos theta minus v cos theta gives you 0, right? The formula for acceleration is change in velocity divided by time. So there is no change in velocity. Horizontally, on the other hand, if I do this, what is going to happen? V sine theta minus V sine theta. So my formula becomes 2V sine theta upon T. So horizontally, my acceleration is 2V sine theta upon T. Vertically, there is no acceleration because velocity at A and B vertically is the same. So when we subtract them, we get our answer as 0. Now, if we go back to our definition of angular velocity, right? Our definition of angular velocity basically stated what? Our definition of angular velocity actually stated that V is equals to r theta upon t. Where am I getting the derivation from? If you remember, we had the formula V equals to r omega, right? So I'm basically getting the derivation from there. Linear velocity is equals to radius multiplied by theta upon t. And I explained to you previously when we went over the topic of linear velocity, how we can get to this equation. So, if I rearrange the equation to make time the subject, the formula becomes r theta upon v is equal to time. This can be substituted in our equation. So, our equation is going to become actually, let's go one step further. Over here, the total angle is not theta. In the diagram, you will see that the angle is 2 theta, right? Theta is the angle between A and C and B and C. But my object is traveling from A to B. So that means my total angle becomes 2 theta. So my time is equals to r 2 theta upon t. This will get substituted over here. Substitution happens, what do we get? 2v sine theta divided by r 2 theta upon t. Okay. Now, when if we decide to solve this as fractions, the lower fraction is going to be flipped upside down and we are going to multiply it. So what does our formula end up becoming? Our formula ends up becoming 2, sorry, 2 and 2 can cancel out actually. So formula becomes v square sine theta divided by r theta. Now, when we go ahead and we're going to talk about it, the next portion is where it gets slightly tricky. This is not the tricky. The next concept is slightly hard to understand. Yes, Ishwish?
I just have a good question. Why is the angle 2 theta now, but then before it was theta only?
Because over here at A, right? Uh, the reason for that is because when I was solving the vectors, so the angle that they were taking was with point C. Okay, so why was it with point C? Because I wanted the angle with the vertical component. I wanted to find out the angle with the vertical component. So this angle theta that is between A and C. Over here, C is basically our the angle between the radius and the horizontal, right? This theta is equal to this theta. Okay, so I'm using it to resolve the individual components, right? If I was, okay. So the thing is that I need the angle between between my velocity and my vertical. Okay. So for this, I need a horizontal reference point or a vertical reference point, right? So, because I am resolving individual vectors over here, I am not looking at A and B as combined. I'm looking at A separately and B separately. Then, over here, the angle theta is not the angular displacement. The angle theta I'm considering over here is not the angle traveled by the object. This is the angle that my linear velocity is making with the projectile, right? So to resolve the vectors, I'm going to use the angle that the velocity is making with the vertical component. I am not talking about the angular displacement. The angular displacement from A to B is, yes, 2 theta. But over here, I'm not considering the angular displacement. I'm resolving vectors. To resolve vectors, I need to know the angle that this component is making with my vertical component, or my linear velocity is making with the vertical component. That's
How
why
did
we
you
only consider.
how did you do like how do you know that the angle is gonna be in that position?
You have to remember your rules of mathematics, right? So 1 second. Let's. This is the angle that radius is making with the vertical. Okay. This is the angle that the radius is making with the vertical. Over here, this is at linear velocity. The object is traveling at linear velocity. Linear velocity is at 90 degrees to the radius. And why is linear velocity at 90 degrees to the radius? That will make more sense when I explain to you centripetal force. Okay. But linear velocity is at 90 degrees to the radius because that is instantaneous velocity. Since this is at 90 degrees to the radius, so if you now resolve it mathematically, this is going to be 90 minus theta. This is going to become theta. This is again going to be 90 minus theta, so this becomes theta, right? Is that making sense? This is the angle of the radius with the vertical. Okay, this is also technically the radius, but this is horizontal. Now, over here, if you consider it, the linear velocity is at 90 degrees to the vertical component, right? Since it is at 90 degrees to the radius, this linear velocity is at 90 degrees to the radius. So this becomes 90 minus theta, and this obviously becomes theta. If this is theta, then this becomes theta, right? Your rules of triangles that you might have studied, I think even in IGCSE physics, sorry, maths. So to go over it again, right? This linear velocity is at 90 degrees to the radius. The angle between this line and this line is theta. So that means that this angle is going to be theta as well, right? You can also use it, the rule of the parallelogram to solve it, parallel lines to solve it. This will become theta. This is going to be 90 minus theta, so this becomes theta. Got it? Making sense?
Yeah. Yeah, makes
Are you
sense.
sure? Okay.
Yeah.
So that is basically how you're getting your theta from. Now, when and the reason, because I'm resolving the vectors, that's why I'm only using theta. Okay. Later on, when we talk about this next portion over here, in this next portion, I am not resolving vectors. What's wrong with this? I'm not resolving vectors. I'm now using the formula angular displacement divided by velocity. So angular displacement is 2. Okay. Now, this let's go ahead. Now, the next part is where it gets slightly tricky. Okay. The next portion is basically this. This formula that you and I have just derived, it must be true for all values of theta, right? Now, we are talking about linear velocity. We are talking about instantaneous velocity, linear velocity. At linear velocity, the theta is at linear sorry, just give me 1 second. In an instantaneous velocity, right? We are talking about instantaneous velocity. So what does over here now, this the physicists, when they were working with the formula, they made an assumption. They said that this value must be true. This formula is true for all values of theta, right? It doesn't matter what the value of theta is, it must be true for all values of theta, meaning that it must be true for extremely small values of theta as well. It must be true for extremely true values of theta as well. Now, if you open up your calculator and you ever decide to do, for example, sine 1, sine 2, sine 3. If you ever do take really small values of sine, you will generally get like a really small answer, right? So they basically, so the scientists said that for really small values of theta, they said for really small values of theta, we can say sine theta upon theta is equals to 1. Again, this was an assumption that they made while doing the derivation, right? This is an assumption. It's not a fact, right? But this is an assumption that the scientist made that for really small that for really small values of theta, if you ever do sine theta upon theta, you generally get your answer as 1. So they assumed, they said, because we know that this formula has to be true for all values of theta, whether they're small or whether they're large. Now, for smaller values, we can safely assume that when we do sine theta divided by theta, the answer generally comes equal to 1. So they said we can say sine theta upon theta is 1. Which again, mathematically, if you ever open up a calculator for you, this might not make sense because because if you, for example, do sine 60 divided by 60, your answer never comes out as 1. But they basically said that we have to assume that this formula is correct for all of the values of theta, whether theta is 90 degrees or whether theta is 0 degrees, right? Because even if an object has no angular displacement, even if an object has not traveled even if an object has not traveled much, it has only traveled 1 degrees, 2 degrees, it will still have acceleration because the velocity is changing, right? When you talk about instantaneous velocity or linear velocity is the velocity at that very specific point. So if I'm measuring instant velocity, obviously the theta is going to be 0. So they said that this formula obviously makes sense for every single value of theta. So if we talk about really small values of theta, and it's again an assumption, it's not something, if you go for it mathematically, it's not going to make a lot of sense. But they made an assumption that for small values of theta, sine theta upon theta is equal to 1. Hence, they got the formula of acceleration as v squared upon r. And this is the final formula that they made. This part, sine theta upon theta, is where I know it gets confusing for a lot of students as well. So the basic logic behind this is that if you decide to solve it mathematically, it's not going to make a lot of sense to you. You are going to wonder, how this can be true, right? But basically, this is an assumption that they had actually made. If you want to go ahead and take a look into it, right? You can take a look into it. This is you probably are going to have to, because this is a mathematical concept. So you are, if you want, you can go ahead and you can take a look into it. You can probably find detailed explanations as to why sine theta upon theta is 1. But this is basically an assumption that was made on the principle that this should apply for all values of theta. And for that means that it should even apply for small values of theta as well. And this is
So
how they
this is
got the
true
final.
for any value of theta.
Yes. That's the assumption. That was their logic. That this formula, this is not true for all values of theta. They said this formula should apply on all values of theta, even for small values. And in cases of small values, sine theta upon theta generally comes somewhere around 1. So they said we will take sine theta upon theta. This does not apply to all values of theta. But they said this formula that we're making, this should apply to all values of theta. So that is how they got the derivation. And then we can further derive it as well, that we know that linear velocity is equals to r omega. So we can substitute that over here, r omega squared divided by r. R squared omega squared upon r is equals to omega squared upon r. So this is a second formula for acceleration. One formula for acceleration is v squared upon r. The second formula for acceleration is omega squared upon r. So these are the two
Would
formulas.
it not be r times w squared?
Sorry?
Would it not be radius times
Yes,
omega
yes,
squared?
yes, 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 yes. R omega squared. Yes, correct. Okay. Now, so this is how you get the derivation of your of your centripetal acceleration. Now, I mentioned to you that over here we have the relationship of 90 degrees. Okay, acceleration. Why was I concerned about the 90-degree angle over here? The reason I was concerned about the 90-degree angle over here is because acceleration always acts towards the center. Acceleration is always towards the center. Why is acceleration towards the center? Reason that acceleration is towards the center is because centripetal force is towards the center. What is centripetal force? Centripetal force is the force that makes the object actually travel in a circular motion. Good example of that is if you go to the amusement park, you go on a roller coaster, or you go to the amusement park and you get on those rides that travel really, really fast in a circle. You will always experience a force that is pulling you towards the center, right? You're always going to experience a force that's going to pull you towards the center. What is that force? Centripetal force. Basically, the object is trying to travel linearly. Object is trying to travel linearly. All right? There is a force pulling it towards the center. The result is that the object goes in a circle. So at every single point, the object is going to be experiencing a force pulling it towards the center. This is why the object goes in a circular manner. So for any object to go in a circular manner, I need a force acting towards the center. There has to be a force acting towards the center. If a planet is orbiting the sun, that is because gravity is providing centripetal force. Gravity is pulling the object towards the center. The object's own velocity is linear. The centripetal force is pulling the object towards the center. The result is that the object travels in a circle. So, and there always has to be a cause of centripetal force. In our planetary system, gravitational force is equal to centripetal force. And this is a very important concept because later on when you do the topic of gravity, I think it's in your unit 5, when you do the topic of gravity, you are going to have to link circular motion and gravitational topic together. Then, if you have tied an object to a string and you are rotating it, the tension in the string is providing the centripetal force. If you have or on an amusement park ride and the object is traveling in a circle, the power from the motor, the force coming from the motor is causing it to travel in a circle, right? So there's always going to be a cause for your centripetal force. If so, there's always going to be cause for centripetal force, and centripetal force always acts towards the center. Similarly, your centripetal acceleration hence also acts towards the center, right? Centripetal force is the resultant force. Okay? Centripetal force is basically considered as the resultant force, and centripetal force always acts towards the center. The object's own velocity acts linearly. The result is that the object goes in a circular movement. So both the centripetal force will always be acting towards the center, and the centripetal acceleration is also going to be acting towards the center. Both those things are always acting towards the center. And we know F is equals to ma. We know that acceleration is v square upon r. So we get the formula F is equals to mv square upon r. This is also a formula for centripetal force, and another formula is omega square r. So centripetal force is equals to mr omega square. So there are two formulas for centripetal force. One is mr omega square, and the other one is going to be mv square upon r. So centripetal force is always going to be acting towards the center. And there's always going to be a cause for the centripetal force that is going to be present. Okay, and so like I give you the example of a gravitational force, then I give you the example of tension in a string. And keep in mind that centripetal force has to be large enough to keep the object traveling in a circular motion. If you remember, I gave you the example of you swinging a rock on with a thread, right? If you keep on swinging it faster and faster and faster and faster and faster, eventually at one point the thread is going to snap off. That is because the tension in the string is no longer uh, producing enough centripetal force to keep the object in a circular motion, right? So centripetal force is always acting towards the center, point number one. So there is always a cause for centripetal force, whether it's tension in a string, whether it is tension in a spring, whether it is a gravitational force, whether it is some kind of magnetic force. There's always a cause. And the whatever the cause is, that has to be large enough that has to be large enough to provide enough centripetal force to keep the object moving, right? So for example, you have got your rock at the end of the string. You're moving it like in a constant speed. Nothing will happen. But as you continue to move it faster and faster and faster and faster, because you're moving it faster, the magnitude of acceleration will increase, right? Obviously, the direction is changing, so acceleration is changing, but magnitude-wise, it remains the same. But the magnitude will also change. And since the magnitude will increase, the required centripetal force increases. At one point, the tension in the string can no longer provide enough centripetal force to keep it in a circular motion. It will snap, the object will fly off. So centripetal force always acts towards the center. Centripetal force is the resultant force that produces centripetal acceleration. And yes, Ashwish?
You also said that the weight is equal to the centripetal force, right?
Sorry, the weight is equals to centripetal
Or like the
force?
gravitational field strength or something.
The gravitational force exerted, for example, the gravitational force that is being exerted by the sun is equal to the centripetal force that's making our planet orbit around it.
Yeah, I see.
Uh, Yeah, I think that is actually it related to the topic itself. Sorry, Ashwish, I'm sorry, were you asking like something related to the gravity thing, or do you want me to elaborate on that, or is that fine?
Yeah, can you elaborate on it, please?
Okay, basically, when you talk about any mass object, okay, every single mass produces gravitational force. Every single mass. You and I, we also produce gravitational force. But gravitational force directly depends upon the mass. Since our mass is so small, technically the gravitational force produced by you and me is completely negligible. But when we talk about large objects like our planets, like our stars, they have the mass is so huge that they are able to produce a gravitational force. Now, gravitational force is always like this. Gravitational force is an attractive force. And a gravitational force is always going to be acting towards the center of the mass. So if this is my sun, this is the gravitational force produced by the sun. It is always going to be acting towards the center of the sun because gravitational force is attractive. It's trying to pull everything towards itself. This is my planet. My planet, let's say, it is traveling in a linear motion. Now, as my planet, and now what is going to happen? My planet is trying to travel linearly. The My planet is trying to travel linearly, and this is actually how your planets and all entered into the orbit of the sun. The planet is trying to travel linearly. Okay, when let's say that it was traveling linearly through space, when it came under the influence of the sun's gravitational field, it was just traveling through space. Right, in space, an object will continue to travel as it is. So it's traveling linearly through space. As it's traveling linearly through space, the gravitational force it comes into the range of sun's gravity. So the sun's gravity is going to pull it towards the center of the planet. But this is a planetary object that obviously also has a large mass. Then it also has its own inertia. It's going to try to travel linearly. The sun's gravitational force is going to pull it towards the center. Hence, the object is going to follow the resultant pathway, which is going to be in a circle. So this is why your planets and all technically, well, yes, the orbit is a bit elliptical and all that, but technically speaking, the object is, this is why our planets move in a circular pathway. Because the sun's gravitational force is pulling the planets towards the center. The planet's own inertia, their own momentum is carrying them linearly. The resultant happens and the object starts to travel in a circular motion. Let's say that the sun is destroyed. If the sun is destroyed, so not going over all the other obvious consequences like the loss of life, if the sun is destroyed, the centripetal force holding our planet in the orbit will disappear because the sun is no longer producing a sufficient gravitational force. As a result, the planet is going to drift off into space linearly. So gravitational force also is so in our planet. The reason our planets are moving in a circular motion is because the centripetal force is coming from the gravity. The gravitational pull of the sun is acting towards the center, and the gravitational pull of the sun is acting as the centripetal force, causing our object to travel in a circular motion. I hope that's making sense. It's a bit more clearer.
Yeah, I understand this, but then also, let's say you were swinging like a rock around,
Yes,
like
yes.
and then the center of the circle that's the rock is moving in. How would that center have like any gravitational field because it has no mass?
In that case, the rock was the example I gave you. The rock was when you had tied it to a string, right? If you've tied it to a string, so obviously there is going to be tension in the string. So the tension in the string is going to produce the centripetal force, right? So centripetal force, whenever an object is moving in a circular motion, there's always a force acting towards the center, that is centripetal force. But centripetal force is not always equal to gravitation. It can be gravitation. In the example of our planet's orbit, the cause of centripetal force is gravity. But if you tie a rock to a piece of a string and you move it in a circle, the tension in the string is producing the centripetal force.
So the tension would be equal to the
Yes,
centripetal force.
exactly, exactly, exactly. So
And then in the
tension
case of the planets, then the gravitational field would be equal
gravitational
to
force,
the.
yes, gravitational force would be equal to the centripetal force. Yes, correct.
Would the gravity of the Earth affect anything? Because then the rock is being pulled towards the Earth. Would that have any effect on the values?
Uh, no, no, no,
Or
no.
is it
So
negligible?
no, 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 no. That's not going to have. Okay. Now over here, you've actually asked me a slightly tricky question. It's not a tricky question, but I will have to go in a bit of detail. When you talk about circular motion, so now it's going to depend on how you're moving the object. If you're moving the object horizontally, then the force of gravity is going to have no effect. If you're moving it horizontally, right, the centripetal force is acting towards the center. The Earth's gravity is acting downwards. So it's actually going to have no effect whatsoever on your motion. But if you move the object in a vertical circular direction, meaning that you are moving it, uh, uh, so one thing is that horizontally, let's say you're moving the rock above your head. Okay, that's horizontal circular motion because you're moving it above your head horizontally. Vertically is if you're moving it in front of you. Okay, up and down, up and down, up and down. In this case, yes, gravity will sort of have an effect. How will it have an effect? When the object is going to be at the top, the centripetal force is also going to be acting towards the center. The weight is also going to be acting towards the center, right? When the object is at the bottom, centripetal force or the tension in the string is going to be acting upwards while the weight is going to be acting downwards. So yes, and there's actually a question that will explain this very well. It's not in your syllabus though, it's from the Cambridge syllabus. I can go over with you in that in the next class. That will really help you understand this concept of vertical circular motion. But the Earth's gravity will only affect it if it will not affect the circular motion per se. But if I have my if I have my string, okay? Now, the tension in the string, when the object is at the bottom, the tension in my string has to provide centripetal force to keep the object moving and also be greater than the weight, right? At the bottom, the tension in the string has to be large enough that it can counteract it can provide the centripetal force needed to keep it in a circular motion and also overcome the weight of the object. This is where the gravity comes into play. So, for example, we were talking about tying our string to a rock and moving it in a circle. At the top, the string is not very likely to break because the weight and the centripetal force are in the same direction. But at the bottom over here, the tension has to be large enough to not only keep it traveling in a circular direction, but also overcome the weight of the object. So this is where the tension, for example, this is where the string will likely break. So in that way, yes, if you're moving the object vertically in a circular motion, gravity of the earth comes into play through weight of the object, right? Through the weight of the object. But in a horizontal direction, it's not going to have that much of an effect.
Yeah, I see. Thank you.
And there's a good, I told you there's a good example question on this. That's not in your syllabus. It's part of the, it was mentioned in the Excel past paper, but it's really good for understanding this concept.
Yeah, thank you,
Okay.
Miss.